So today we're going to think about what we can learn by observing the light coming from stars. So there's lots of stars in the world, um, in the universe. Yeah. And you can see in this picture of just like a stars in the sky. The differences that you can spot is that some stars are smaller and larger. Some stars have different colors. Some are redder, some are bluer, some are yellower. Um, And so when we really get down to it, the thing that makes stars look different is their color, and their size. They have a different magnitude as well. That's how bright they are. We're not actually going to get into that in distance learning, but we are going to talk about this difference of the color. And so you can think about, well, probably the color can tell you some stuff about the stars, and that's what we're going to be looking at. Astronomers have been looking at the spectra of stars for a long time. Humans have been looking at the color of stars for a long time too. But we're going to get into this thing called the spectra or spectrum of the star. It's called a spectrum when it's singular, spectra when it's plural. And the way that we look at these is that we take the incoming starlight, or even sunlight, which is also starlight, and spread it out to examine each different wavelength. You can use a prism to do this. So you can think about sunlight coming into a prism and you get a rainbow. This is essentially just examining that rainbow really closely. We can also use diffraction gratings, and that's what we use today in modern science. And we actually use diffraction gratings in class to look at some spectra of some gases that I'll talk a little bit more about later. So different stars have different spectra. You can see some different stars here. These are actually the 7 different classes of stars. And they all have some subtle differences. You notice probably some similarities. But we're going to be thinking today about what do these differences tell us about the stars. We can look at that stellar spectra in a different way, in a graphical way, where we not only have the frequency or wavelength of that light, but we also have plotted here the intensity. So we can see that it has a peak intensity, and then it kind of falls off, and all stars sort of have a similar curve. But why do stars even create light? Like, why do they shine? Seems like a pretty basic question. And I bet you can say, Ms. Getz, I know that. It's because there's nuclear fusion happening inside them. And you're right, there is nuclear fusion happening inside them that produces extremely high energy photons. And those high energy photons randomly bounce back and forth inside the star, running into atoms, bouncing back and forth for actually a really, really, really long time, until eventually they get to the photosphere of the atom, of the star. I'm sorry, they get to the photosphere of the star, and again they're running into atoms. And when an electron in an atom receives energy, it jumps up to an energy level by some amount. And stars have this process happening constantly, due to the nuclear fusion that is causing them to have a very high temperature because of the energy released by the nuclear fusion. And so this electron that gets more energy doesn't hang out there forever. So something with high energy, like a photon of light from that nuclear fusion, hits the atom, hits the electron, causes it to go up an energy level. It is an excited electron now. And then at some point, the electron falls back down and it emits that same frequency of light. We saw this with the hydrogen spectrum, and I believe we looked at a couple other spectra in class, but I don't remember entirely. But if we ionize this hydrogen tube, which I think we did in class, and we look through diffraction gratings, we can see the spectrum of hydrogen. And we can see that there's a red line and a blue line and some purple lines. And we looked at this in class. You can actually measure what wavelengths these are using some laws of diffraction and some stuff you already know about waves. We're not going to do that in distance learning, but we are going to think about this spectrum because it can help us really understand what's happening inside of stars and why different stars look a little bit different. So there's this way to find the energy of a specific frequency of a photon. So if you have a photon's frequency or wavelength, because you can switch between the two, you can multiply it by this constant h. It's called Planck's constant. And my IB packet, I see that it is 6.63 times 10 to the negative 34 joule seconds. And Planck's constant helps us think about, helps relate energy and frequency, as you can tell by this equation. We can also do some substitution and have that equation be in terms of wavelength. Pretty great. So here I have a simplified picture of the energy levels of an atom. So you remember from chemistry that atoms have a closest to the nucleus energy level, next energy level up, next energy level up. You can think about these kind of as those orbitals. And so there's all of these different types of transitions that are possible. You can have an electron up here on energy level 5 and it falls back down to the ground state and that'll give off some light. You can have an electron up here at level 5 and it just falls back to level 3 and it will also give off some light and the light will be different. So we want to be able to think about which of these different transitions of electrons falling from one state to the next, level 5 to level 2, level 3 to level 1, which one would have the largest wavelength, which one would have the smallest wavelength. So pause the video for a second and try to sort of work this out for yourself. Okay, so first you're going to want to consider which will have the most energy. The most energy. Well, most energy would probably be like the biggest arrow, right? Like, because these are the energy levels. So the biggest arrow would be from level 5 to level 1. That's the most energy. Okay, then how does energy and wavelength relate to each other? Well, if I look at my equation over here, I see that energy is inversely proportional to wavelength because wavelength is in the denominator. So that means energy is opposite of wavelength. So if this has the most energy, that means it would have opposite of wavelength, smallest wavelength. Biggest energy, smallest wavelength. So this would be the smallest wavelength, and that means that the largest wavelength then would be the one that had the least energy, or this little tiny transition. Let's see if I'm right. Oh, I am right. Oh, cool. And so you can see that these are actually all labeled with their wavelengths. They're labeled with wavelength in nanometers. That's going to be your BFF. Check out your IB packet if you don't know the conversion. And so we can actually see that these specific wavelengths that we can see with our eyeballs are only ones that are going to the second level, which is kind of interesting. Why don't we see these other energy transitions, do you think? Any guesses? I hope you have a guess, because I'm not going to go into it right now. Instead, I want to talk about the different ways that we're going to see these spectra. So this is hydrogen spectra, it's just hydrogen gas, but there's different ways we're going to be looking at spectra. There's continuous spectrums of light, and this is what you might think of as sunlight. Sunlight technically actually has some absorption lights, but let's not get into that right now. And so this is where you're going to see that full rainbow of all of the different wavelengths of electromagnetic radiation. Then we have these things called emission line spectra, and these are where you see individual lines of color, and that's like what we just saw here. This is called a hydrogen emission tube, so it has an emission line spectra. And then we have absorption line spectrums, and those are where you see lines missing. So there's like this black line. And in astronomy, these come up in different times. So astronomers see emission lines in stellar spectra. So we can see here in this spectra of a star, there's these little peaks, and these are emission lines where there's a specific element that is emitting that particular wavelength of light. You also see emission lines in nebulas because they're hot glowing gas. And so hot glowing gas emits specific lines of radiation because it is the gas that is glowing. It's not an overall object that is glowing, it's the individual atoms of gas, and we can actually see those and tell what gases they are based on the different colors, the different lines that we see in the spectra. Absorption line spectra we also see in stellar spectra. So here we have this stellar spectra, and you can see that there's these little holes. These little holes come from light being absorbed, and this light is absorbed by some gas. So when you have a light shining and there's some gas in the way, The light shines through the gas and some lines get absorbed. We see here. So these lines get absorbed. And you also see these in nebula. We have some gas that's blocking some of the starlight from more distant stars, causing them to not get through. We also see this when we look at our star's spectrum through the Earth's atmosphere. And so here I can see, so this is the our star spectrum, and there are these little spots where here on Earth, we don't get those specific wavelengths because they're absorbed by ozone and water and CO2 in our atmosphere. So why is it that an atom absorbs light? So in this absorption spectrum, if an atom of cold gas absorbs light, it's going to emit that same amount back, that same light back. So it's kind of weird that you get these lines showing up. So I find this GIF really helpful in understanding that. So you've got some gas here between you and the star, and the star's light came, and some of the light was absorbed. This orange light was absorbed. And notice that when the orange light is absorbed, that means that your emission here that you get from the star is missing that. So that means there's some of the light has been absorbed, and that light that this atom has absorbed, notice the atom re-emits it, it goes out in a different direction. And so the key idea here is that atoms absorb light and re-emit it in any direction. And so if you have some atoms of a cold gas here in between you and a star or you and a light, that light that is absorbed by the gas is going to get re-emitted in a random direction. And so you're not necessarily going to see it, which is what causes this absorption line, or rather missing light that you aren't seeing from the star. Cool. So this still doesn't really tell you why it's different colors. Okay. So here's our sun spectrum. It's pretty cool. We have both the visual representation of the different colors that we see and the intensity spectrum. Pretty great. Here's another star. Here's another star. Wow. Here's a bunch of different stars. You can see that they all have some similarities, but they all have some differences. Kind of hard to really understand what's happening here. And so what we're going to do is we're going to think about some radiation laws, and I'm actually going to have you do a little lab up next to try to learn one of these radiation laws. And we're going to do that by really thinking about, well, what does it mean when something is glowing? So you've seen things glowing here on Earth. Maybe you have an electric stove or have seen an electric stove that glows. And we can explain things glowing using something called the black body model. And your stove, and if you have an electric stove, is a very good example of a black body model. And black body model is a way that helps us think about stars and other hot things, or things with any temperature actually. But it's an ideal model because it's saying that in this model, the object is going to emit 100% of the energy it absorbs. And in real life, that's obviously not true, but that makes this model a lot easier to use and will really help you think about why are different things different colors, what exactly is happening with them. And so we're going to do an investigation that in class we would spend like 20 minutes on. You have as much time as you need, but 20 minutes is about how much time I would imagine it would take, maybe 30. During this lab, you're going to want to pay close attention to the patterns that you're noticing. So I'm going to actually do a little preview of the lab website. So you're going to get to this lab website. I think the first thing on the lab worksheet asks you to make it be a light bulb. So I've changed the little slider to be set to light bulb. And now notice my graph looks crappy and it's hard to read. You can zoom in on your different axes. So I'm going to actually zoom in on my spectral power intensity. It's just watts per meter squared. So that's just the intensity. You've learned about that before. Anyway, so you can zoom in that way. As I change what it is again, you can zoom in, you can zoom out. And so that's really helpful. You can also put on graph values. That's really nice. And labels so you know which part of the spectrum you're looking at. And it has this little picture here that helps you visualize what is happening. So do your best.